Before I begin part C, you may want to quickly take a second to check your answers to the table in part B, either using my diagram so you can see where all my areas came from, or by simply checking my table so you can see what I got as I added or accumulated each subsequent section. As a reminder, you can also have a tab open with the answer key in the learning plan so that you can check your answers as you go, especially if you're skipping ahead in some of the videos or figuring out some of these things on your own. Nevertheless, we are going to persist on to letter C, and we're going to continue our idea of using this area problem to help us understand what's going on. Now in letter C, we've already noted that the fundamental theorem exists. So this little fact is just reinforcing that if you have to take a derivative of an integral, you're back at the original function, just with x plugged into your dummy variable. That's all that that's saying. Now, you might be wondering where that's coming from. Like, why does that have anything to do with this snowfall problem? Why does that have anything to do with the area? Think about what this table, though, wants you to find. This table wants you to find big F prime. And we are reiterating here that if we need to find big F prime, we need to go back to what we already know about big F. Big F prime refers to the derivative of big F, but big F was an area problem. So the derivative of big F is the derivative of this area problem. And that's why the fundamental theorem comes in, because the derivative of an area doesn't really make that much sense in context, but the derivative of an integral does. The derivative of an integral is going to cancel itself out. That's the fundamental theorem again. So big F prime, the derivative of big F, is like the derivative of the integral. And if you picture those two things canceling out, the derivative and the integral symbol canceling out, all you're left with is little f, and if you plug in the dummy variable as x, little f of x. Notice what we just established though. Big F prime is the same as little f. So if the table wants me to find big F prime values, that's really like saying it wants me to find little f values. And in case you're thinking, okay, so what's the point of that? Remember, we have a graph. If we have a graph, little f values are literally just points on this graph. So instead of thinking of big F prime as some complicated version of area somehow, let's think of big F prime instead as little f. So I'm not going to think about big F prime. I'm going to kind of cross that out mentally. I'm going to focus on little f. Little f is just points on the graph, specifically y coordinates on the graph. And if I can think of this as y coordinates, now this table is going to read a little bit differently. If this is a table full of y coordinates, I'm not going to do anything fancy. I'm just looking at the graph and write down the y coordinates that I see. Now I've highlighted all over the graph, so I need to do my best to not distract myself by those highlights. I am just looking for y coordinates on the graph. At 0, the y coordinate on the graph is 1. Boom. At 1, the y coordinate on the graph is 3. Boom. At 2, the y coordinate on the graph is 3. Boom. So I'm not reinventing the wheel here. I'm not even thinking about this as an area problem, because it's not. Big F prime is not an area problem. Big F is an area problem, but as soon as you take the derivative, it's no longer an area problem because it's no longer an integral. When you take the derivative of an integral, you've canceled those two operations out. What you're left with is just a normal function. And the normal function left over is the normal function little f, which is a normal graph that we can read like normal people read graphs. We just read for the y coordinates. So take some time to make sure that this concept makes sense, and then finish the table by reading the y coordinates off the graph.